Hello, everybody, and welcome back to Physics Rich, your one-stop channel for the preparation of IIT-JEE Mains, Advanced, NEET, and also AP. Today, we are back with Awesomeologist series on Bernoulli's theorem. My dear students, this series is for those students who are looking forwards to enhancing their understanding in Bernoulli's theorem. Now, to understand this series, you should have gone through the theory lectures, which I've already uploaded in another playlist. I have uploaded lectures for fluid statics and fluid dynamics alike, where I have explained all the concepts from the very scratch. If you want to understand everything from the very scratch, from the very basics, and build your understanding to a medium level, then go to the theory lectures. And then you will be most welcome to watch the Awesomeologist series, where we will become the doctors of awesome things. And the awesome thing that we are discussing today is Bernoulli's theorem. Guys, this is the second lecture in this series. If you watched the first lecture, great. If you haven't watched it, I highly recommend you check it out. I will put the link in the description. And let's begin with the second part of our Awesomeologist series. So guys, we are discussing about Bernoulli's theorem. And in the first part, I discussed with you this beautiful problem from a very nice book called, can you guess what that book is? Put in the comments if you know which book I have taken this question from. So at this point 1 and at this point 2, we were comparing the pressures, and we saw that this is a horizontal tube. It has been made vertically, but it's actually horizontal. At point 1, there is a higher velocity, and at point 2, there is a lesser velocity, because at point 2, there is a higher pressure. We have discussed in every detail as to why this happens. And then we came to a very important conclusion that wherever the velocity is high, the streamlines are crowded, and where the velocity is low, the streamlines are loosely spaced apart. Okay? And then we moved on to this problem where we understood the importance of applying the Bernoulli's equation and the equation of continuity at the same time. Here we see that there is a certain amount of fluid which is flowing through this pipe. It is flowing through this lesser cross-section area and a greater cross-section area both. And because of varying pressures at these two places, the amount of liquid in this fluid column is different. Here there is a higher pressure, here there is a lesser pressure. And again, wherever there is a lesser pressure, you have a higher velocity. And where you have a more pressure, you have lesser velocity, as we saw in the previous question by the application of Bernoulli's equation. And here again, we see the same thing, that there are more crowded streamlines. So there's a higher velocity. And because there's a higher velocity, more energy is going into this region, where this is the energy is going into more of movement than less of static pressure. Okay, so there is a less pressure over here, which is why the height of the liquid column is less. And again, over here, there's a larger liquid column because the pressure over here is more. Now, continuing upon these ideas which we have already built upon, we will try this problem. Okay, and over here, what do we have? We have a fluid which is flowing in this manner. All right, and this fluid could be anything. This could be water, this could be petroleum, this could be petrol, diesel, something. Okay, it's flowing over here. And what we have done is that we have poked a hole in this pipe, and this tube goes inside and turns towards the left. Okay, and then this tube also goes around and then hits this pipe again at a different location. One interesting thing that we have done is that we have put another fluid over here. And this other fluid has a density of sigma. Okay, this is a sigma. Okay, not the kind of sigma, this is in Greek, it's a small sigma. Okay, so this is the density of this other fluid. Let me just write this down, is the density of other fluid. All right, it's the density of this fluid. Now, this fluid and this fluid are obviously non-miscible. They will not dissolve into each other. All right. Now, what we are looking for is, with what velocity is the fluid flowing over here? That's the problem that we are looking to solve. We want to find out what is the speed of flow. So, what can we do? So my dear students, let's draw streamlines. You see that there will be a streamline that will come over here, but this particle will understand one thing, that the fluid over here is not flowing. And when there is no fluid flow, there is no streamline. Because essentially, what exactly is a streamline? Guys, streamline is defined as an imaginary curve. Very importantly, it's an imaginary curve. In fluids, these lines don't really exist. These are geometrical constructions. These are not real. These are geometrical constructions that we use to understand how the fluid flows. And streamlines are made in such a way that if you go to the streamline at any point along its trajectory, wherever it is, you go to that point and you draw a tangent over there. The fluid particle would be having a velocity along that tangent. Okay, so if I am drawing a streamline that looks like this, then at any point I can draw a tangent, and at that tangential point I will have a certain velocity of my fluid particle. Over here, the direction is here. Over here, the direction is here. Over here, the direction is here. But does the streamline, one single streamline, does it tell you about the magnitude of the velocity? Does it tell you about the amount of velocity it has? And the answer is no, it does not. Then what tells us about the magnitude of velocity? Well, whether or not if the streamlines are crowded or spaced apart. If they are crowded, it's fast. If they are spaced apart, it's slow. So here we have a streamline, and this part of the fluid does not seem to be flowing. It seems to be stagnant. Let me use the word again, stagnant. Stagnant. What is the meaning of the word stagnant? Stagnant means that which does not flow. Okay, stagnant means that which does not flow. If you have some water reservoir behind your house and rain happens and then water is just stuck over there for 10 days, that's stagnant water. Okay, so this is stagnant water because it's not flowing. So the streamline that exists over here will come and will notice, oh, the water seems to be stagnant in the pipe, in this pipe. So it will take a U-turn and it will leave. And guys, you obviously know one thing from kinematics. If a particle goes and returns back, at one point of time, there has to be a point where its velocity becomes zero. You have studied about this in something as simple as motion in one dimension. If I throw this pen up and if I catch it, at the highest point, its velocity is zero, because at that point exactly, it is going to return back. It changes its direction. When it changes its direction, its velocity is supposed to be zero. So guys, what will we do? We will take a point over here, A, and take another point over here, B. Okay, and at A and B, you can apply Bernoulli's theorem. You can say that pressure at A plus half rho velocity at A square. Well, this is the standard method of applying Bernoulli's equation. Pressure at B plus half rho VB square. And again, guys, I would say that if you do not know that this is how Bernoulli's equation is written, head towards the theory lectures. You will definitely find it very easy to understand this. Now, this is the Bernoulli's equation applied for point A and point B. We can also apply the Bernoulli's equation for another streamline that happens to go from this point. Now, I am talking about this point C and another point over here A dash. Okay, so I'm going to say that pressure at A dash plus half rho velocity at A dash squared equals pressure at C plus half rho velocity at C squared. This is again the same thing I've written for this other streamline. Now you see, guys, if you find a book that says that you can apply Bernoulli's equation between point B and C, take that book, close it, and throw it away, because that's teaching you wrong things. You cannot apply Bernoulli's equation between point B and C. You can apply it between A and B and between A dash and C, because you can only apply Bernoulli's equation for points that are on the same streamline. Okay? Now, here's the thing. Why is it that these books that teach you wrong things, they say that pressure, the that at point B and C you can apply Bernoulli's. Why is it that they still get the right answer? They get the right answer because A and A dash are actually similar points. They are similar points as in they have very similar properties. They have the same pressure and they have the same velocity, which means that for both these two equations, equation 1 and equation 2, the LHS is the same, guys. And then if I equate the RHS, it becomes PB plus half rho VB square equals to PC plus half rho VC square. This appears as if I have applied Bernoulli's between B and C. Do you get it now? Because it appears so, that's why some people will tell you, some teachers will tell you, some books will tell you that you can apply between B and C, but you can't. Conceptually, you can't. Okay. So, with the help of 1 and 2, equating the RHS, we get this. One very interesting thing is that this term, do you see this term? I just explained to you why this term is 0. Because the particle changes its direction. So, VB is 0. VB is 0. And that's why I can simply say that the pressure at B should be equal to pressure at C plus half rho VC squared. So pressure at B is greater than pressure at C, which we can notice from this equation. Well, it kind of makes sense because half rho VC square cannot be negative. So pressure at C plus something is pressure at B. So this pressure at C must be lesser than the pressure at B. Make sense? Makes sense? Up until now, all things are nice and easy. Now, you see guys that because of these pressure values, what do we notice? We notice that a higher pressure inside this has caused this white fluid to be pushed downwards, whereas a lesser pressure on this side has caused this fluid to be pushed not so downwards. So let's say if this height is H1, pressure at C has only been able to push it by H1, whereas what is this? This is H2. So you can clearly see that pressure at B has been able to push this white liquid down by H2. So that's why you can say that pressure at B can be written as sigma GH2. Please mind it that this is static pressure. Pressure at B is static pressure. Okay. Some people might tell you that this is the dynamic pressure. Actually, it is not. It is the static pressure. And also, for the point C, what can you say? For the point C, you can say that pressure at point C will be equal to sigma GH1. All right. Now, we can say that pressure at point B minus pressure at point C is equal to half rho VC square. Also, one very important thing, guys, that this VC, the velocity at the C is the velocity of the flow. So essentially, we are looking for VC, and VC is our final answer. So pressure at B minus pressure at C becomes sigma GH2 minus sigma GH1, and that is half rho VC squared. I will take the H2 minus H1 out from here, and I'll take the 2 on this side and I'll take the rho on this side, and this becomes VC squared. And guys, H2 minus H1 was given to us in the question as delta H. So we simply get VC squared equals to 2 sigma by rho G delta H, and that gives us the flow velocity squared. And what is our full answer? The full answer will simply be 2 sigma by rho, G delta H raised to 1 by 2. That's our final answer. Okay. And you will find these kind of problems occurring in fluid dynamics every now and then. Every now and then you will find them. Okay. So let's move to the next question. I hope you enjoyed learning about this. It was a very beautiful question. Now we have an application of what we learned previously. It's kind of like that, kind of like an application of what we learned previously. check this out. What's happening here? There's a fluid that enters with V equals to 2.5 meters per second. Okay. And then there is a certain velocity with which the fluid exits over here. A certain velocity with which the fluid exits over here. And he's asking us that what will be the height to which this fountain will sort of rise? Okay. That is our question. And now we are supposed to solve it. So how shall we proceed? And as usual, what shall we do? We shall apply the Bernoulli's equation. Let's figure out how to apply the Bernoulli's equation in this situation. Shall we take a streamline? How shall we take a streamline? We shall make a streamline that looks like this. Okay? We shall make a streamline that looks like this. All right? Now, in this streamline, what can we say? We can say that let's call this point A and let's call this point B. Okay? So let's apply Bernoulli's equation between point A and B. So what can we say? Pressure at point A plus half rho VA squared plus rho GHA equals pressure at point B plus half rho VB squared plus rho GHB. Okay. Let's see if we can work with this. So we can assume a few things first. Firstly, this depth is negligible because this is not given in the question, so we will assume it to be negligible. Because if you start including this, then we'll need the data, but we don't have the data. Secondly, we also have to assume that the static pressure at point A and point B has to be equal. See, what is happening at point B? This point B is like at the end of this streamline. And what it means is that right after the fluid goes out, then we can assume that the streamline sort of ends over here. Okay. And after that, we cannot really say how the edges of this hole are, and because of these corners, maybe there is some mixing of the fluid and maybe there's some turbulence. So we cannot really apply Bernoulli's theorem beyond this point B. Okay. So we have to understand that the pressure at A and pressure at B must be equal to the atmospheric pressure. Okay. So this pressure at A, pressure at B, and atmospheric pressure P naught are supposed to be taken to be equal, and that's why we will cancel these terms out. Secondly, at the point A, like I said, that this height is negligible because it's not given in the question. We will assume that this term is also equal to 0. So now we are left with half rho VA square equals to half rho VB square plus rho GH of the point B. And this H is given to you as H naught. Okay. Now you can clearly see that the rho also gets cancelled. Rho, 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 row, row, row the boat gently in the stream. Merrily, merrily, life is just a dream. Yeah, that was the nursery rhyme. Okay, the rho, rho, rho gets cancelled. So VA square equals to VB square plus 2GH naught. Now again, I implore you guys, this is not the third equation of motion. This is the Bernoulli's theorem. And we have found this from conservation of energy. This is not V square equals to U square plus 2AS. Please do not get confused. Okay, so VA square equals to VB square plus 2GH naught. What are we looking for, guys? We're looking for this VB square. All right. So do we have VA square? Yes, sir, we do. We have VA square. Can I just write it over here, this side? Or can I just shift my calculations? Oh, no, I can't. I'm going to have to write it on this side, guys. Okay, let me write over here. So I get VA square minus 2GH naught equals to VB square. Okay. And when my particle comes out of this with a velocity of VB, okay, so don't you think that this is just like motion in one dimension now? Okay, this is just like motion in one dimension where if I throw a particle up with a speed u, it attains a maximum height of u square upon 2g, right? So if this is thrown up with VB square, then the height h that it should gain is nothing but VB square upon 2g. Where have we taken this equation from? We have taken this equation from motion in one dimension, where we have learned that if a particle is thrown up with a velocity v, it attains a height of total h. And how do we find that? Now this you can find using the equation, the third equation of motion, which is v square equals to u square plus 2as, where this is the final velocity, or rather I should write it as vf square equals to vi square plus 2as, or in fact not s but h, and in fact not a but minus g, because this is acceleration due to gravity. Now, what is the Vf? Vf is 0, so that's why I get Vi square equals to 2gh, and the h comes out to be Vi square upon 2g. What is our Vi? Vi means the initial velocity, Vf means the final velocity, which means that if our velocity over here is Vb, then this just simply becomes Vb square upon 2g, right? And that's what we are looking for. We are looking for Vb square upon 2g. So why don't we do one thing? We just divide the entire equation with 2g, and that is our answer, h. So ultimately, I am supposed to find out Va square upon 2g minus h naught. So what am I supposed to find? Let me just write over here that I'm looking for Va square upon 2g minus h naught. What is Va? It's 2.5. 2.5. It's in meters per second. Yes. Always check that the units should always be in your SI. Okay, standard international units. What is h naught? H naught is, oh, it's 12 centimeters. Very nice. This is 12 centimeters. So 12 upon 100. So this whole thing is in meters. Now I want my answer in centimeters, so I shall multiply this entire thing with 100. So now we are left with a little bit of calculation. So what do we have here, guys? We have 2.5 squared is 6.25. In case you don't know it, 25 squared is 625. So 2.5 squared is 6.25. Divide that with 20 minus 12 upon 100. And the whole thing is supposed to be multiplied with 100. And if we solve it further, what do we get? We get 6.25 divided by 20 times 100 minus 12. This 100 and this 100 will get cancelled. This 20 and this 100 will get cancelled with 5. And I have a 6.25 times 5. 6.25 times 5 minus 12. So what do I have? I suppose this will be 31.25, right? Yeah, some of you may not believe me. You can try multiplying this yourself. 6.25 times 5 will be 31.25. This is 31.25 minus 12, and I think this answer is slightly lesser than 20. It seems that we have a 19.25 centimeters. That is our answer. And I'll tell you what, if you take this 10 close to 9.8, if you don't take G as 10 and if you take it as 9.8, then perhaps you will get an answer closer to 20. Okay, so yeah, that was it. So I hope you enjoyed both these questions, guys. We have more questions to do. I have this one very beautiful problem, and then I will like to end this with this absolutely amazing problem, which I will do in the third part. And guys, thank you for watching. Stay physics rich. All the best.